Okay, let's go and get started today. We have a lot to get through. I don't quite have the midterms done yet. I actually have them graded, but I have one of them that was still needing to be completed. So as soon as I get those graded and recorded, I'll get those back to you and I'll send out an email to let you know. We're probably going to meet in class on Wednesday and we'll go over them then. But today I want to get through some material, and we have a lot to get through, so let's go and get started. Today we're going to be doing error detection and error correction, and we'll talk about why that's important here in a second. Now, the reason why it's important starts with this problem statement. You have the transmitter sending a message. If you remember back to that diagram where we had the transmitter, the receiver, and the channel in between. The transmitter sends a message by encoding it on the channel. The receiver pulls it off the channel and decodes it. And ideally, the message that goes in from the transmitter is the message that comes out to the receiver. And that's not always the case, though, because if you remember, the channel is susceptible to noise or interference or other outside influence. And that means that transmission and reception, they're not always perfectly reliable. In other words, the message you send could be corrupted during transmission and then be different than the message that actually gets received. So the question is, how do we know that the message was transferred correctly? What can we do to make sure that what was received was actually what was sent? And you can see how important that would be. There's a big difference between, let's say you send somebody like, should we attack? And go and no are just one character different, but there's a big difference between go and attack somebody or no, don't. And so it's important to have some way of verifying that the message that was sent was the same as the one that was actually received on the end. But how do we know that? Well, the key to that, the key to detecting errors and the key to correcting errors is redundancy. And so to detect errors, we need redundancy. And so the question is why? And let's think about that for a second. Why would we need redundancy? And redundancy is essentially repeating something. And the reason we need redundancy is if we're going to compare the message with something to know if the message is correct or not, we need to have something to compare it to, which means we have to have a repetition of the message or some form of the message that's summarized so that we know that what we're receiving is what it's supposed to be. And if you think about that, human languages actually have redundancies built in. The English, for example, is 70% to 90% redundant. And it depends on if it's written or spoken, what level that is. Written language has less redundancy than spoken language. Spoken language tends to have more redundancy. And why is that? And the reason that is, humans naturally will talk in a way that has additional redundancy when you're speaking as compared to when you're writing, which is why people's spoken vocabulary is smaller than their written vocabulary. And it's probably because you tend to simplify the message, add redundancy when you're speaking. The reason why is to help convey a point. So even as I'm saying this to you over this lecture, I'm repeating certain phrases multiple times. Look up here, redundancies, redundant, redundancy. You'll notice that that phrase is repeated multiple times in slightly different ways. And the reason for that is to get the message across, to make sure that what I'm saying is the ideas that are coming out of my head are ultimately being turned into sound, which is ultimately going into your ears and being turned back into ideas. And I want to make sure those ideas get through. So there's redundancy that's added, additional ways of saying the same thing, ways of repeating the same thing. But just any English sentence itself has redundancy built in without even having multiple sentences like this. And one of the ways that you can measure that from an information standpoint is to kind of play a game where you guess the letter that's going to come next. Or maybe you would guess the word that's going to come next. And if you can guess, we'll play it with the letter version of it here, but if you can guess the letter that was going to be the next one, then it was really unnecessary and it was redundant. It was something you could have guessed. So in other words, if you could have probabilistically picked what the next character was going to be, then there wasn't really any reason to have it because you could just assume that's what it was going to be. So let's play that game with this sentence here. So here's a sentence, and we might start wanting to guess what the letters are and see if we can guess them. So guessing the first letter, well, you might play the odds and pick T, for example, and you would be right. The first letter is T. And then we go on, and notice I'm color coding these. The ones that are correct I'm going to put in green. The ones that we couldn't guess are going to be in red. And then we might try to guess the next letter, or next few letters, in this case T-H-E. Okay, so we got all three of those. Those are green. And then maybe we continue that process. Red is ones where we didn't guess. Maybe we guessed a space and said it was an R. But if you were to go through and play this game with somebody else, where you pick a phrase like this, and then have them guess the letters, give them the ones that they guess, write them in green, the ones that they don't, write them in red, and then you were to count up how many they could have guessed correctly versus how many they couldn't have guessed, then you're going to end up with something that shows the redundancy level. So in this case, when I played this game with a group of people, they guessed 26 out of the 36. They needed 10, and I have them shown here in which ones are red and which ones are green. But that comes out to be 72% redundant. In other words, you could guess more than 2/3 of the letters and symbols in this sentence. Now, there could be sentences that are more complicated or more surprising that would be harder to guess. But once they got T-H-E, they guessed space. It was an R. Once you have the R, you know it's an E. There's a space after that. And then this is going to be is, or some other kind of verb phrase. So is, it turned out to be space. And then here they guessed something else, and it's N. And then after N, they guessed wrong, and it was an O. So no. And then they said, well, that's probably, there is no, so space. And then R, E, V. Most people here probably would have guessed the E at that point, but they picked something else. And I had to give them the rest of this, but reverse, space, on, space, A, space, and then M-O-T you had to be given, but then after you have M-O-T, it's probably motorcycle, and they write out the rest of it. And then it says, we know that there's one character left, probably a period, could be an exclamation mark, could be a question mark. But notice that 72% redundant for this example. Now, what is the reason for all this? You might think, well, it's just 2/3 or more of what you're saying, maybe even up to 90% of what you're saying is just pointless. It's redundant. But it's not pointless. It's there for error detection and error correction. So why do human languages have so much redundancy? Because it has built-in error detection and error correction. So that way a listener or a reader can be sure that they are getting the message. And that's true even if parts of that message are blanked something P during transmission. And you might, depending on who you are, be able to figure out what this, notice parts of that get messed up, but you can figure out that this is messed up, or maybe you thought this was something else up. That's okay. I kind of did that on purpose. But note that you can still figure out what the gist of the sentence is, even though parts are missing. And the reason is because of the redundancy that surrounds those parts. And that's what we're going to want to do with our communication. So how do we add redundancy in our communication? Well, the first thing, redundancy just means repeating something. So we might start with repetition of some sort. So in this case, we have a simple repetition code where we say our message is hello, question mark. We just double up every letter. So instead of H, we send H twice, E twice, L, 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 O, O, question mark, question mark. And on the receiving end, we say we're receiving these in pairs. If we ever get a pair that doesn't match, we know there's an error with that one. So that would allow us to identify errors when they occur. If I get something that doesn't match the previous character, I know there was an error in that one. I don't know which of the two is wrong or which of the two is right. It could be the error code that's wrong. Could be the previous or the error detection repetition is wrong, or the character itself. But we know something is wrong there. Now, one thing to note about this, though, is notice that we're wasting half, or I'll say using instead of wasting. We're using half of our bandwidth for error detection. In other words, we're doubling the length of the message. Hello turned into twice as many characters as it was before to do that. So that's fairly inefficient. So what we're going to see going forward is we want to move to something that doesn't waste as much bandwidth, but can still detect when errors occur. We don't want to double the size of our message. We maybe want to increase it just a little bit, but we're going to have to increase it some in order to have redundancy. We're going to have to repeat something. So let's look at some other ways. So here's the parity is probably the simplest form of error detection. And the idea there is we add an extra bit to every serial data unit that we're sending, or every, you can think, data block that we're sending. So in this case, there are really kind of two types. There are actually more than two types that I'll mention briefly, but I'm not going to focus on those because they're not really error detection. But even parity, we add a bit that makes the number of ones even. Odd parity, we add a bit that makes the number of ones odd. So our example is, here's the letter capital A. It represented in 8 bits, 0, 1, 0, 0, 0, 0, 0, 1. So for even parity, it already has 2 bits set high, so we would put it to 0 to leave it at an even number. If it were odd parity, we put it at a 1 to make it 3 instead of 2 to make it an odd number. The other two types of parity, well, 3 types of parity that you might encounter are, there's what's called mark parity, where it's always a 1 in that extra position. There's space parity, where it's always a 0 in that extra position. And those aren't really a form of error detection. They're just an extra bit that is either a 1 or a 0 always. And then there's no parity, where there's no parity bit at all. But that's not a kind of error detection either. So when you see a kind of parity that's actually meant to do error detection, you'll see this extra bit that's added. And this is actually used quite a bit because it's so simple. You can make a logic circuit that just says, hey, are there an even number of bits or an odd number of bits? And outputs a 1 or a 0. And actually computer RAM, when you have a memory module that's plugged into your motherboard or in your laptop, a lot of times those have 9 bits or an extra bit beyond just the data bits, and that's a parity bit to detect if something goes wrong with that memory cell. The computer can know this memory cell is damaged in some way. It's not working right. So one thing to note is, relative to our repetition code we saw earlier, parity uses only 1/9 of the bandwidth for redundancy. And you can tell that because there's 9 total bits, 8 data, 1 parity. It's 1/9 of the bandwidth is being used, rather than 50% of it. We have less than 10% of it. Or I guess it's slightly more than 10% of it. But parity will detect all single bit errors. So if we have any one bit that changes here, parity will detect it. But parity is a little bit weak in that if we have multiple errors, like this goes to a 1 and that goes to a 1, then the parity bit will not detect a multi-bit error. Or if this goes to a 0 and that goes to a 1, it will not detect that. So it will detect all single bit errors, and it will detect all errors that affect an odd number of bits. But if we have an error that affects an even number of bits, we can't detect it with parity. It's not good enough to do that. All right, there is another form of parity that adds a little bit to that, and that's called block parity. And block parity, what it does is it computes parity bits just like we did before, but it does it both horizontally, going across each of these patterns, but then it also does it in a block going down. And that block size could be 8, or in this case 6. It could be much longer than that. But let's go ahead and look at what the block parity for this would look like. And I did even here for this example, hello exclamation mark. So here's the horizontal parity going down here, and here's the vertical parity going across there as a parity byte. But you'll notice that this now, if I have an offsetting or an offsetting error like here and here, that will also affect the row and column. So we will detect more of those errors. So if I have an error on any one of these that affects an even number of bits, I'll still detect it on the vertical rather than the horizontal. And the same thing vice versa. So this can detect more errors. It can also be used to correct any single bit error, because if I have a single bit change value, I'll see the parity will be wrong here and it'll be wrong there. And I know if I have it wrong in just one row and one column, then I can fix and undo that and put it back to what it should have been. And that's a form of error correction, which we'll talk about later on in the lecture. So block parity can detect and correct all single bit errors. It can detect all errors that affect different rows and columns in odd numbers of bits. Some errors can be offsetting and will go undetected. But it does have the advantage of being easy to implement, very easy to implement. And so there are systems that use block parity because of that. But it's still, there can be offsetting errors that will go undetected. For example, see this block of ones and zeros here? Imagine that the 1 goes over there, this 1 goes over there, the other ones are 0, so those just kind of switch places. Then we will miss that because the parity will still be correct this way. It'll still be correct that way, that way, that way. So you could have this H become whatever that would be, and the E become whatever that would be, and it would still get through. All right, let's look at some other methods quickly. Arithmetic checksum. In arithmetic checksum, basically you treat all of the bytes as if they were individual values, either in a block of a certain size or the entire message, and then you just add them all up. And then to limit the size of that sum, because the sum will grow and grow and grow as the message grows, maybe you would use modulus to limit that to get an 8-bit checksum or 16-bit checksum or something like that. So let's look at an example of how this would work. So here's our same message, hello. Here are the byte values for that. So we just add all those up. And in this case, we end up with 405. But 405 won't fit in a single byte if we wanted an 8-bit checksum. So we mod by 256. And if you remember what mod does, it gives you the remainder of a division. So we're dividing 405 by 256. But all we care about is the remainder. And the remainder of a division of any number is going to be between 0 and 1 less than that number. So this is guaranteed to give us a resulting value that's in the range 0 to 255, which will fit in 1 byte. In this case, it comes out to be 149. So that's our 8-bit checksum that comes out of this. And notice we could grow that message, and we'd still get a number in the range 0 to 255 in this case. And if we wanted something that had a little more resolution, we could do a 2-byte checksum and mod by, instead of 256, we could mod by 65,536, which would give us a number 0 to 65,535, which would be what we would get with a 16-bit checksum. And we could even do 32-bit checksums. But the idea here is we just sum all these up, mod by whatever the size we want, and then that gives us our resulting check value. Now the idea is when you would transmit that message, you would send the message, and then you'd send the checksum. And then on the receiving end, they would receive the message and the checksum. They would compute their own version of the checksum. And if their sum matches your sum, they say, hey, it's probably the message is good. Now, that probably, though, can be a little bit concerning because, note, you can still have offsetting errors. So, for example, in this case here, IDLLO, so H goes 1 higher, E goes 1 less. This becomes 73. This becomes 68. We still get the same sum of 405. So you can have things that still are corrupted or wrong that still make it through this. It's not perfect. And offsetting errors affecting groups of bytes might be fairly common. This works a little better than parity, but it's still not perfect. It still lets things get through. And for example, if we have an 8-bit checksum, it'll catch 93% of errors, but there's still 7% that are left. We go up to a 16-bit checksum, we do a little bit better. We'll look at that later on today. But note that it's not perfect. You can still have offsetting errors. So that takes us to this technique that is really widely used, and it's actually very clever. It's a beautiful technique. But what it is called CRC. And what a CRC is a cyclic redundancy check. And you'll notice some things about that name. Redundancy, that's what we're after with error detection. Check is just like a checksum. It's something we're going to check against. But cyclic means something that's repeating over and over and over again. It's a process that's going to kind of repeat itself. And the way those work is they work like a checksum, but rather than using addition, which can allow offsetting errors to go undetected relatively easily, add 1 here, subtract 1 there, get the same checksum. But they work like performing long division on the binary message instead of an arithmetic sum. And what they're going to do with that long division is they're going to use the remainder of the long division as the CRC value or as the check value. So the value that we divide into the message is called the generator. So in other words, we're taking the message as if it's a really long binary number, and we're dividing into it this generator number, a specially chosen number called the generator. And then what happens is as we divide that in, we're going to, whatever pops out as the remainder after that giant long division, that's our CRC value. Now, it's not quite a full division in the sense of it being an arithmetic division. To simplify it, we use what's called modulo 2 arithmetic. And what modulo 2 arithmetic does is basically has no borrows and no carries. And because of that, that means we can implement it using just the XOR operation. And the XOR is a really kind of cool process to use, because XOR has a instruction in almost every CPU that has ever been created all the way since the beginning of microprocessors and computer systems. So XOR is a logic operation that's incredibly fast. We don't have to worry about carries and borrows. It's going to be fast even on simple microprocessors and microcontrollers. Now, the idea is the same as with a checksum, meaning that you send the value, that same value is received. You calculate it again on reception. If the one you calculated on the receiver matches the one that you received from the transmitter, then you're pretty sure that there are no errors. And one of the cool things about this being cyclic in nature, or a cyclic redundancy check, is any error that happens at any stage in the process will perturb or disrupt all subsequent steps. So in other words, if you think about how long division works, you have this kind of working value. That the way long division works is this divides into that makes this number that you started with change, and then you move the next digit down, and that makes the number change, and then you feed it back in, and that. So any change that happens early on ripples it all the way down to the end of the process. So let's go ahead and take a look at that in the next slide here. So hold on one second, then we're going to look at an example. Okay, so let's go ahead and take a look at the an example of a CRC, and hopefully it'll make a little more sense. So let's start off with a message. We're going to make this a really simple CRC just to make it easy to follow along. But we're going to take the message hi exclamation mark. So capital H, lowercase I, exclamation mark. And if you look at those in decimal, 72, 105, 33, those look like this in binary. So we're going to make that one big long binary number. And then what we're going to do is we're going to pad that at the end by the length of the generator. And in our case, we're going to use just a 4-bit generator to make it easy to follow. And when we pad it by that generator, the message comes out to be this, that number of bits minus 1. So 4 bits minus 1 is 3. We add 3 zeros on the end. So here's my entire message. So notice here's the H. Actually, 1, 0, 0. That should be a 1. Okay, so somehow this is messed up. Okay, well, apparently when I typed this in here, I messed this up. So that could be wrong in the example going forward, but the process will be correct. So just bear with me. Hopefully I didn't screw that up too badly, but this is wrong here. In fact, I might go ahead and pause right now and see about fixing that. So give me a second here. Okay, I fixed that. It was actually a problem up here, not down here in the message. So this being an even number, could not have a 1 in that last place, so I just had that. So I fixed that. So all these run together, looks like this. And there's my 3 bits worth of padding on the end. So there's my 3 bits worth of padding on the end. So let's go through this example. So here's the rule. We take our generator, we start out with zeros, and what we do is we add 1 bit at a time to the end of those zeros, and what we do is we're going to add bits from the message to the end of our CRC. So our CRC value we can consider as it starting out with the first 4 bits. You can consider it starting out with a 0, and you just add the bits to the end as you go. When a 1 ends up in the 4th position, or bit 0, 1, 2, the 3rd position over, the 4th one over from the right, when we get a 1 bit in that position, then we XOR by the generator. So this generator will come down here and XOR whenever we get a 1 in the most significant position. And if there's a 0 in the most significant position, we just add another bit to the end. So in other words, we're going to bring the next bit down, bring the next one down, and we're going to keep doing that until we get a 1 in the position of the most significant bit of the generator. And when we do that, we XOR, and that's it. That's how this works. What's going to happen is that process is going to continue until we get where we've moved the last bit down over here. And then the value that's left in the padding bit area over here, that becomes our CRC value. So when we go through all of the bits, including the padding bits, we now have our CRC value. So let's go through and perform this. So here we started out with the CRC value matching the first 4 bits here. But notice there's not a 1 in the 4th position. So we're going to bring down the next one, which I highlighted there. And now we have 1, 0, 0, 1. Well, now we have a 1 in the most significant position. So we're going to XOR. So we XOR by our generator. And we remember what XOR does. If they're the same, we get a 0. If they're different, we get a 1. So in this case, it matches exactly. So we get all zeros. And now we're going to start bringing down more zeros. We're going to bring down the next one, and the next one, and the next one, and the next one. And we still don't have a 1 in the most significant position. So the next one, the next one, the next one, the next one. Now we have 1, 1, 0, 1. Now we have a 1 in that position, the 4th position over. So now we're going to XOR again. XOR by our generator again. And in this case, we're going to get 0, 1, 0, 0. We don't have anything in the most significant position, so we need to bring down another 0. Now we do. XOR again. And that gives us a result of 0, 0, 0, 1. And now we're going to bring down the next 3 bits. So now we have 1, 0, 1, 0. XOR by 1, 0, 0, 1. Because we had a 1 in that position. And that's going to give us 0, 0, 1, 1. Bring down the next 2. 1, 1, 0, 1. XOR by 1, 0, 0, 1. We get 1, 0, 0. Bring down the next 0. Now we have 1,000. 1, 0, 0, 0. XOR by that. We get 1. Bring down the next 3 zeros. And I just shifted all that up now so we can see more of it, because I didn't plan ahead for my font size when I was creating this. So now we XOR by 1, 0, 0, 1 again, which gives us 0, 0, 0, 1. Now we're going to bring down the 1. Bring down the 0, bring down the 0, and XOR 1, 1, 0, 0 by 1, 0, 0, 1, which gives me 0, 1, 0, 1. And then we bring down the last 0, and since we brought down the last 0, we stop. So our CRC value is 1, 0, 1, 0 at that point. Now there are some variations on this algorithm that we showed here. In other words, rather than starting with all zeros, there are some of these that start with the inversion of the CRC generator when it starts, and then there's some that at the end, when we get to the padding bits, they'll do one more XOR at the end. But really the process is the same. Now you'll notice that there are really only 2 different operations that are performed here. It's XORing something or shifting to the left and adding a bit, which makes this perfect for implementing in a really efficient way on a microprocessor. You either XOR one value by another value, the CRC by the generator, or you shift the CRC over and add another bit on the end. Shift, add a bit, shift, add a bit, shift, add a bit, XOR. Shift, add a bit, XOR. Shift, add a bit, shift, add a bit, XOR. It's this really, you make a really tight loop that does this incredibly quickly. And goes through and adds bit after bit after bit, XORing when necessary. But when you're done, you have this CRC value. Now the cool thing is, if something goes wrong or the value is different by just 1 bit, you'll notice it'll affect every subsequent step going down here. The error will ripple through and be magnified by the future errors. So it's much harder in this case to have an offsetting error that will undo what happened earlier, like we had with an arithmetic checksum. All right, so how effective are CRCs? Well, let's look at the other 2. First off, parity, if you remember, will catch all 1-bit errors and odd bit numbers of errors, but even bit numbers of errors it'll miss completely. Checksums, an 8-bit checksum is 93% effective, meaning it'll catch 93% of errors, but that leaves a whopping 7% of errors will just go undetected. 16-bit checksums are about 97% effective, and 32-bit checksums are about 99% effective. But the reason why it's not perfect is you can still have those offsetting errors. Add 1 here, take 1 away there. Add 5 here, take 5 away there. Have the most significant bit flip here to 128, but flip the other way somewhere else and take away 128. Those kinds of errors will always make it through an arithmetic checksum. But with a CRC, with it having that effect of that feedback loop where it takes the value, feeds it back in, shifts it over, feeds it back in, they're much more effective. So let's look at CRCs. With an 8-bit CRC, it's 99.9999999% of errors will get detected by it. A 16-bit CRC is even more effective. So notice how small that percentage of errors it will make it through it. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's 15 nines there on the end of that 99. So in other words, 1 to the 15th or negative 15th is 1 in 1 to the 15th is how many errors could make it through. That's a chance that an error would make it through. And with a 32-bit CRC, now we have I think that's 24 nines there. So CRCs are incredibly effective. They're easy to compute and efficient to compute, but way more effective than we would ever get with something like an arithmetic checksum. A little bit more complicated, but not too much. So because of that, CRCs are used everywhere. For example, there are some standard generators that tend to be used. CRC 8 uses the generator starting, it's an 8-bit CRC rather than the weird 4-bit thing we did for our example. But you'll notice that the generator for that would be 0xD5. The CRC that's used as the standard for Bluetooth communication is A7. It's also an 8-bit CRC. And then there's some other ones. The CRC 16 CCITT. That is a standard one that's used a lot. It has this generator. There's another one that IBM uses that is this hex 8005. And CRC32, a standard for that, uses this generator. There are a whole bunch of other ones as well. And really, the generator with a different, just like with long division, a different generator will give a different resulting remainder at the end. Same thing is true for CRCs, a different generator. So when you're making a communication system that uses CRCs, you have to make sure the generator you're using on this transmitter matches the one on the receiver. And I would suggest if you ever have to do some kind of check that requires high reliability, consider using our CRC because they're easy to calculate. The code to calculate them is really efficient, but they're very effective at catching errors. And in fact, the internet itself uses CRCs for packets. Wi-Fi networks use CRCs for wireless traffic and so forth. Okay, so now we're on to error correction, which goes one step further. So we've looked at parity, block parity, arithmetic checksums, and cyclic redundancy checks. And those are good for detecting errors. But what if we want to not just detect an error, but correct it when it happens? So in other words, we want the error to happen, or if an error does happen, we need to fix it in some way. So method 1 is what's called an automatic repeat request. And really, that just makes use of error detection, the techniques we already saw. And it will give a negative acknowledge, meaning, hey, that failed, I need you to send that again. So in other words, you send a message. The receiving end, if it detects a checksum failure or a CRC failure, it sends a message back saying, I didn't get that, I need it again. If it is received correctly, then we would send an ACK, or yes, I got that, everything's good, go to the next one. So that re-request, though, that requires being able to send that back to the transmitter, requires a duplex communication. In other words, we have to have a back channel where we can talk back to the sender to say, yes, I got that, or no, I didn't. And there are some different types of automatic repeat requests, which are called ARQ, an acronym ARQ, or ARC. So let's look at some of those different types of automatic repeat request. So types of them are stop and wait. And what stop and wait does is we send a single data frame on the transmitter and we wait for it either an ACK or an ACK. If we get an ACK, we go to the next thing and send the next data frame. And then we wait for an ACK. If we get an ACK, we resend the same one that we already sent. So in other words, we repeat the one and then do that. Now, that could be slow over a long communication where you send one, wait for the response, get the response. So there are some alternate ways of doing that, where there's a technique of automatic repeat request called go back in. And what that does is you have a sliding window of a certain number of frames. And when you ACK, you send back the sequence number of packet up to which all data has been received. So in other words, you might have a sliding window of 10 packets that are out there. And if somebody sends back an ACK, says ACK 10, that means they got all 10 of them okay, up to 10. And then you can go to the next 10. But if they say ACK up to 8, then you would send 9 and 10 again. And then they would ACK 10, and then you could go on from there. But as soon as they ACKed up to 8, you could send 8 more packets. So you could have 9, 10, 11, 12, 13, 14. And so that can make things much more efficient because you have, you're not sending one, waiting, send the next one, wait. You're sending a group of them, and you're managing that sliding window of multiple frames of a certain size. There's also what's called selective repeat, where the NAC only requests missing or damaged sequence numbers and then re-requests them as necessary. So in other words, you might send 10 frames, and if only frame 6 was damaged, then you say NAC 6, they resend 6. But all of those methods still require error detection of some sort, and they also all require us to be able to have a back channel to the transmitter to re-request anything that's damaged or missing in those sequences of blocks of data that are being sent. But there are cases where we don't have a back channel, which we're going to look at in a second. So first off, automatic repeat request requires a few things. It has redundancy in the form of some sort of error detecting code. Could be an arithmetic checksum, could be a cyclic redundancy check, could be block parity, could be whatever. It's usually a CRC. It also requires duplex communication, which means that we have to be able to re-request or damaged packets and a way to acknowledge packets that are good. So we need two-way communication via a back channel back to the transmitter. We also have to have some protocol that says how do we deal with re-requesting? What does the transmitter do when it gets a negative acknowledge with a packet number? What is the process for that? How's it supposed to work? And we're going to talk more about protocols here in a little bit. Not tonight, but in subsequent classes. Now, while ARQ is used in a lot of systems, there are cases where using a back channel is either inconvenient or it's impossible. What do we do about those cases? And what are some cases where it is difficult? Let's talk about that, like satellite communication. You have your satellite TV, like a direct TV or dish network. It can't really request things back from the satellite in a stream of data that's coming down because it's just the satellite is just transmitting this stream of data to all people at the same time. Same with if you have a Sirius radio, like a satellite radio, XM radio. I don't even know, are both of those still things? I think they one bought out the other. I don't know which one's which. But anyway, something like satellite communication, where it's a one-way communication from the satellite to many receivers. And you don't really have the chance to say, hey, I missed part of that, or send that again. Another example would be spacecraft, where the distance is too great to make re-requests convenient. So you have, I don't know, like the rover that's on Mars. How would you ever send a re-request for a small packet of data? CDs and DVDs. As you're playing a CD or a DVD or a Blu-ray disc, if there's dust on there, you don't want it to disrupt your whole stream of data that's coming off of there. You want it to be able to continue and kind of reconstruct what was missing. And then other optical systems like QR codes or IR communication systems will often have some sort of error correction built into them as well. And the reason being that there's no back channel. It's hard to re-request, and that's especially true for streaming data like satellite TVs or CDs or DVDs or Blu-ray discs. But also notice with QR codes, it's like you're reading that, and if part of it's covered or obscured or part of it has a glare on it, you still want to be able to detect what the message is that's coming off of that. So how do we do that? Well, how can we deal with error correction without a back channel and without the ability to have a request to repeat something? And the answer to that is more redundancy. So redundancy. We want to add even more redundancy to it so we can reconstruct parts that are missing, not just detect when things are. So in order to do that, we're going to have to use redundancy in a different way than we used it for error detection. So we're going to use it to try to detect the errors, but also fix the errors when we find them. And that is using the redundancy in a special way that's called an error correcting code, or ECC is what those are commonly called. And the way an ECC works, or an error correcting code works, is there are really two types. We'll talk about those more, but like a forward error correcting code is a name for an error correcting code. So sometimes you'll see it referred to as FEC, forward error codes. And what that forward means is that essentially means there's no back channel. There's no you're just taking the stream of data, and given that stream of data, if there's errors in it, we can correct them as long as it's not too messed up. So redundant information is added into the channel. There's enough redundancy that allows the message to be reconstructed if errors are detected. No back channel is required. Works with simplex communication. But note that not all errors can always be corrected. That there could be errors that are so messed up that we can't reconstruct what it was supposed to be. All right, now examples of forward error correcting codes. Well, those exist in the English language as well. So you'll notice that, and maybe I should have showed this one thing at a time, but you'll notice here, if I gave you this, you probably couldn't figure it out, but if I gave you the second or third one, I'm pretty sure you could probably figure out what this message says. And notice that this is not just detecting something is wrong in the form of something is missing. You can actually fill that in. So you can fill this in. If I had this one covered up, you could say, Carpe diem, seize the day, boys, make your lives extraordinary. You could figure that out without having the letters plugged in. You can just figure it out because of the redundancy that's built into the English language. And one thing to note is if the error rate is too high, redundancy isn't enough to allow the correction. So for example, this top one, you probably couldn't figure out what the message was from this because the error rate is too high. If I took out all of the characters and only left like this capital M, there'd be no way for you to figure out what that says. So with many errors, the correction is difficult or impossible, like this. But with fewer errors, correction becomes impossible. So if I give you this, you could figure that out to infinity and beyond. So a higher level of redundancy allows for correction of messages with higher error rates. A lower level of redundancy allows us to correct things with low error rates. So there's a trade-off or a balance between high levels of redundancy and how much extra, in other words, how much extra data we have to add and how much we can reconstruct when something's missing. There's also a difference in the algorithm that we would use to do that correction. So we've actually seen forward error correcting codes before with that repetition codes, where we could say, what if instead of sending each character once or twice, we send it 3 times? H, 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 E, 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 L, 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 O, 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 exclamation mark, exclamation mark. And the idea here is if we have just one of these that gets corrupted, like H, Z, H, we say I have 2 H's, I'm going to say it's an H. So 2 out of the 3, we say if two of them match, we go with that as the thing we can correct the one that was missing. And we also saw it with block parity. Single bit errors could always be corrected automatically in block parity. Also notice that ARQ and forward error correcting codes can be used together. In other words, you could have a system that corrects things, but if it's too messed up, then it re-requests it. So you cut down on the amount you have to use the back channel that way. All right, so that's usually called a hybrid ECC or hybrid error correcting code, where you use both an ARQ and a forward error correcting code together. FEC can fix a lot of the errors. If the message is too damaged, then we fall back to a re-request via ARQ. So that hybrid approach can have benefits of not polluting the back channel with a lot of bandwidth use, but when it's absolutely necessary, you say, hey, I need that repeated. So there are systems that use that. All right, now there's kind of several types of forward error correcting code. One is called a block code, which works on fixed size blocks of data. Examples of that are what's called Reed-Solomon coding, which is used in CDs and DVDs. GOLE, LDPC, which is a low density parity check, multi-dimensional parity and Hamming codes. There's also a thing that's called a convolution code, which works on a stream of data or arbitrary data lengths rather than a fixed block size. Some examples of that are the Viterbi encoding and what are called turbo codes, which are Viterbi are used in spacecraft and Mars rovers. Turbo codes are used in kind of the cell network. And the cell network is another case where you have data packets that are transmitting that are sound. You can't really have a request because it's a stream of audio. So you don't want to have the audio get delayed. So you transmit that audio data with encoded as a stream of data that's encoded with this turbo code, and if parts of it get corrupted or messed up, it just fixes it as it goes. All right, so we're going to look at one example. And this you can tell from this slide, this is a very rich area. There's a lot of stuff. We could spend an entire lecture on Reed-Solomon coding or GOLE codes or low density parity checks. We could actually have an entire class in forward error correcting codes. We could have a whole course in that. But we're not going to do that in this class because we got other things I want to get to this semester. But just note that they all rely on redundancy. They all rely on being able to reconstruct the message with parts of the data missing by using that redundancy. But let's look at one type that's relatively simple and easy to understand. And we can look at how it works. So there's this thing called Hamming codes that are simple to implement. They can correct all single bit errors in a block. They can detect all 2-bit errors in a block. They used a fixed size block of bits. And the way they work is they basically use a concept that's similar to parity, but they use overlapping parity calculations. And essentially, all bits that are powers of 2 are used to store the parity bits. So rather than sticking it at the end, we're putting them throughout the message in different places. All the other bits end up being data bits. So let's take a look at how this would work. So if we look at a Hamming code with 4 parity bits, that would give us 4 parity bits and 11 data bits, which is in kind of the Hamming code lingo is called 1511. So in other words, 11 is the data bits, 15 is the total length of the word that's being sent. So that puts parity bits as the first bit position, the second bit position, 4th and 8th bit position. Notice these are all powers of 2 bit positions, and all the other bit positions are data bits. So that looks like this. So here's our parity bits, P1, P2, P4, and P8. And then here's the data bits, D1, D2, D3, D4, D5, D6, D7, D8, D9, D10, D11. And I started using the counting numbers or the natural numbers here rather than starting with index of 0 just to make it easier. So you'll notice that allows us to count up, hey, there's 15 bits. But note that if you're looking online at stuff about Hamming codes, it might start out with bit position 0. I just use the natural numbers to make it easier to say, look, there's 15 total bits, and 1, 2, 3, 4 of them are parity, and there are 11 data bits. Now, the way that this works is parity, being in bit position 1, it skips by groups of the bit position sizes. This is the ones place, so we skip every other one. So this parity bit 1 covers that position, skip 1, that one, skip 1, that one, skip 1, that one. So you'll notice that it counts all of the bits. It will always skip over the other parity bits. It won't count them as part of the check, but it will count itself as part of that. So we either make that even or odd, probably even in our case. So it's just a parity calculation just like we did before, but it's every other bit including itself in that parity check. Now, if we go to parity bit 2, that's the 2's place, it starts with itself, and then it's every 2. So those 2, skip 2, these 2, skip 2, these 2, skip 2, those 2. Notice again, it skips over all the other parity ones. And then if we look at parity bit 4, it goes in groups of 4. And then parity bit 8 does all these. But you'll notice that that gives us kind of this unique signature of which one, which bit is covered by which parity. And if you'll notice, each one is it has at least 2 parity bits covering it. Like D1 has P1 and P2 covering it. D2 has P1 and P4. D3 has P2 and P4. D4 has 1, 2, and 4. D5 has these 2. D6 has those 2. D7 has those ones. And so forth all the way up to D11 has all the parity bits. And that kind of overlapping parity coverage ensures that there's a unique set of parity bit coverage for every bit in that block. Which means that if one of these bits is damaged and has the wrong value, we can tell which one it is because it's the one based on the parity coverage. So for single bit errors, that arrangement ensures that a unique set of parity bits will cover each bit in the block. The sum of the parity bits in error indicate the bit that is in error. It's a very clever technique. Let's go back and look at that. So you notice, let's say that parity bit, let's say 1 and 4 came up wrong. So if 1 and 4 came up wrong, 1 plus 4 is 5. That means bit 5 is the one in error. So in other words, bit 5 has 1 and 4. Bit 6 has 2 and 4. 7 has 4, 2, and 1. So 4, 5, 6, 7. And D11, if you look at that, that's 8 plus 4 plus 2 plus 1. So 8 plus 4 is 12, 13, 14, 15. So that's bit position 15 is the one in error. And if the parity bit comes out to the position comes out to be on one of the parity bits, that means the parity bit itself is an error. So they're kind of checking themselves too. So if a single bit parity is an error, then that parity bit is the error. Very, very clever method of reconstructing when single bits can get lost from things. And these Hamming codes are used on digital tape for tape backup storage. But notice that that technique can be used for parity blocks of different sizes. The one we looked at was 1511, but you could also do 7-4. You could do 3126, 6357, which has 6 parity bits with 57 data bits, 63 total bits. And you'll notice these always come out to be the total number of bits is 1 less than a power of 2 number of total bits, which is useful. Because a 64-bit block, you could have 63 total bits, 57 of them would be data, 6 would be parity. And you could extend that on to 7 parity bits or 8 parity bits as necessary. Now, there are other types of error correcting code, or forward error correction, but the key concept there is that, and I would encourage you, if you're interested in those, to look up like Reed-Solomon coding. When you listen to a CD, there can be a fairly good sized scratch on that CD and it'll play the music flawlessly. Or if you have a DVD where the tracks are even closer together, a speck of dust might wipe out a large block of data, but it'll still play the movie just fine. How does it do that? It uses redundancy to reconstruct the missing portions of that message. And since errors tend to happen in bursts, Some forward error correction systems use a technique called interleaving to spread the continuous parts of the message around to different areas before encoding. And there are wireless systems that do that as well. But the idea there is to show you kind of how that would work. Is let's say we want to send this message hello. We encode it with redundancy by doing that. But then if we have a block error where it was continuous, which burst errors tend to be, that wipes out 4 characters, it will wipe out all of these E's and part of the H. We couldn't reconstruct that. So note that the damaged H could be recovered, but the E cannot. But if we used interleaving, we might do something like this. We have this message with our redundancy added, and then we interleave it. We basically H-E-L-L-O, we kind of interleave it so it's spread out like this. And now a burst error would hit that, but when we de-interleave it, we now get this, H-H-H-E-E-E blank L-L blank L-L blank O-O blank exclamation mark, and now we can reconstruct that. So that interleaving technique, there's a method of doing that where you kind of zigzag across the, you make a block of the bits and you zigzag across them, or you go, rather than this way, you go up and down through columns and then back and forth through them. And by doing that, you're spreading out the things that would normally be in a stream together in time. You're spreading it out, and then on the receiving end, you de-interleave it. And that's especially useful for wireless things where there might be a burst of noise that happens from a spark or lightning, and that would wipe out a block of data that's contiguous, like we have here. But by interleaving it, you spread out the redundant parts of it and put different parts of the message in such a way that it only affects things that are far apart in that de-interleave code, which can be really useful. Also very smart. And like I said, there are other types of forward error correction. The one I said that you might want to take a look at would be Reed-Solomon codes. Those are used in all kinds of things from CDs, QR codes, spacecraft. A lot of the spacecraft use those for picture data that they're sending back, or other scientific data they're sending back. But the properties of Reed-Solomon codes, it adds T number of symbols of check data to a block, which allows it to detect up to T error symbols. So in other words, the number of bits worth of check data you add is how many bits worth of errors you can detect. And it can correct up to 1/2 that number of errors. So in other words, if you have a block of data, let's say, I don't know, let's say 1K, so 1024 bytes, and you were to add to that a block of another 512 bytes, you could have up to half of that 1K block get totally destroyed, and you could still detect that there was an error in there. And you could actually have up to half of that block size, so half of 512, you could have up to 128 bits get destroyed, and you could fix them. So it's actually, the cool thing about that, it's tunable to the amount of desired error correction by how big you make the block of check data. So you could actually make the block of check data bigger than the data itself, twice as big as the data itself, and you could correct or fix any errors that happened in that. Now, keep in mind that the errors could also affect the check data itself. So if you have too many errors, you still won't be able to do that because you're still transmitting the check block. But that kind of thing, Reed-Solomon codes, they're beyond the scope of what I want to cover today. It's mathematically more difficult than the Hamming codes, but it's similar in that it uses redundancy in this clever way, so when things get destroyed, they can be fixed. Or detected and fixed. All right, so that gets us to, I'm not going to cover more of those other methods in great detail, but there are a lot of powerful, useful, and interesting forward error correcting codes. One of the main takeaways I wanted you to get from this class was the power of redundancy in a communication system, and CRCs, and at least some conceptual understanding of how you do an error correcting code. And most wireless systems now, like the GSM network for cell phones, cell phone communication, or like the wireless for the Wi-Fi network, they use some sort of forward error correcting code as part of that. And the reason for that is because notice you can cut down greatly on the amount of back and forth you need for ARQ protocols when things get lost, and you can also have successful communication even in the midst of a very noisy channel environment. So the channel could be incredibly noisy and you can still get data through. One type of network that uses that, or like a wireless network, is like a LoRa wireless communication uses that. And LoRa is a long-range wireless technology that works with very low power over very long distances, but they encode the data with this incredibly high redundancy rate that allows it to have, even if there's a lot of it gets destroyed or lost or is not detectable, it can still reconstruct the message. So this stuff is really useful for a lot of different application areas. Okay, that's all for today. Everybody stay safe. Next class, I'll be probably be sending out an email, and we'll go over the midterm exam. But that's it for today. And I came in at just about an hour, which is where I wanted to come in with this material. If you want, go back and review some of the stuff, things that are going to be incredibly useful to you going forward in your career, understanding CRCs. And actually, that wireless module we used earlier in the semester, that NRF2401P module that you guys got to communicate, it actually has a CRC capability built into the hardware for it, that it can verify packets automatically for you. It doesn't have any forward error correction, but it does have an automatic acknowledgement mode and a CRC built into it. All right, so that's it. And I'll see you guys next time, probably in class next time to go over the midterm when I hand them back. That's it.